Hello, I'm Edward Tarte, math teacher. This is another in a series of solution videos to some of my math challenges. The math challenge for this solution video is my Pythagorean challenge. In that original video, I presented the most important formula in all of math, the Pythagorean equation. It is about a right triangle, that is a triangle with a right angle. If the lengths of the legs, the two sides forming the right angle, are A and B, and the length of the third side, known as the hypotenuse, is C, we have this all-important formula, A squared plus B squared equals C squared, meaning A times A plus B times B equals C times C. In that original video, I gave a proof of this formula, and then I gave the following challenge. This is to discover groups of three counting numbers. Counting numbers means 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on indefinitely. Groups of three counting numbers that satisfy the Pythagorean equation. In other words, you need to find three square numbers where two of them added equal the third one. Here's my suggestion. Make a table with an x column on the left and an x squared on the column, x squared, the column on the right. Number the x column from 1 to 25, and beside each x, multiply it by itself to get x squared. 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9, and so in the x squared column you'll have a list of square numbers. Next, find the differences in the x squared column. The difference between 1 and 4 is 3, that is 1 plus 3 is 4. The difference between 4 and 9 is 5, that is 4 plus 5 is 9. That gives us addition statements. And we need an addition statement where a square number plus a square number equals a square number. This one doesn't quite work. 4 is a square number and so is 9, but 5 isn't. And so we cannot use 4 plus 5 equals 9. We need all three of them to be square numbers, and if you have the x's go down to 25, you'll find some examples. When you find an example, determine what the A, the B, and the C is, what they are, and put them in another table like this, so that you'll have an A, a B, and a C, three counting numbers that satisfy the Pythagorean equation. We call numbers like that Pythagorean triples. So try to get a list of some Pythagorean triples. Then look for some kind of significant pattern in your list. Specifically, you'll have an A, a B, and a C. Ask yourself, what can I do to my A to get my B and my C? But if you can discover a significant pattern in this table, then try this challenge. Find a Pythagorean triple where the smallest of the three numbers is 1,213. Here's my solution. I have here a table of square numbers there in the x squared column, going from 1 squared to 14 squared. And as I suggested in the original video, I have a list of their differences here, 3, 5, 7, 9, 11, and so on. We notice that the differences are consecutive odd numbers. Now we're looking for a square number plus a square number equals a square number. The first square number we come to in the differences column is 9. And we have this addition fact. 9 plus 16 equals 25. That's 3 squared plus 4 squared equals 5 squared. That means 3, 4, and 5 can be the lengths of the sides of a right triangle. The legs having lengths 3 and 4, the hypotenuse having length 5. That comes from the first square number that we find in the differences column. The next square number after 9 is 16, but 16 is even. These numbers are all odd. The next odd square number after 9 is 25. We see that in the x squared column. So we look for 25 in the differences column. It's here. And that gives us this addition fact: 25 plus 144 equals 169. That is, 5 squared plus 12 squared equals 13 squared. We see that here. 5 squared plus 12 squared equals 13 squared. That is representing a 5, 12, 13 right triangle. So we can have a right triangle with legs of length 5 and 12 and hypotenuse length 13. And so I enter those results in an ABC table. A being, in each case, the smallest of the three numbers. So we have this ABC triple, 3, 4, 5. We call that a Pythagorean triple. And our next Pythagorean triple, 5, 12, 13. If we continue our x squared table further, the next square number we come to in the differences column is 49, and here is that portion of the table. This gives us the addition fact: 49 plus 576 equals 625. That gives us the ABC group 7, which is the square root of 49, 24, 25. Continuing down the x squared table, the next square number we come to in the differences column is 81, giving us this addition fact: 81 plus 1,600 equals 1,681. That gives us the Pythagorean triple 9, which is the square root of 81, 40, 41. So we have two more entries in the ABC table. So here are our 4 entries thus far in our ABC table, gotten from our x squared and differences table. 3, 4, 5, 5, 12, 13, 7, 24, 25, and 9, 40, 41. Now we look for a pattern. Specifically, is there something we can do to each A to get the B and C that go with us? I notice that 4 plus 5 is 9, and 9 is 3 squared. 12 plus 13 is 25. 25 is 5 squared. 24 plus 25 is 49. 49 is 7 squared. 40 plus 41 is 81. 81 is 9 squared. That is a consistent pattern. So what can we do to 3 to get 4 and 5, to 5 to get 12 and 13, and so on? If I square the 3, I get 9. If I divide 9 by 2, I get 4.5. I subtract a half from that and I get 4. I add a half to that and I get 5. That is, 3 squared is 9. 9 divided by 2 is 4.5. 4.5 minus a half is 4. 4.5 plus a half is 5. And it works in all the others. 5 squared is 25. 25 divided by 2 is 12.5. We have 12 and 13. 7 squared is 49. Half of 49 is 24.5. We have 24 and 25. 9 squared is 81. 81 divided by 2 is 40.5, giving us 40.5. and 41. Just to check out the next two examples, 3, 5, 7, 9, the next A would be 11. 11 squared is 121. 121 divided by 2 is 60 and a half. Take half away and add a half, we have 60 and 61. The next odd number is 13. 13 squared is 169. 169 divided by 2 is 84 and a half. Take away a half and add a half, we have 84 and 85. And we can verify, either by hand or by a calculator, that 11 squared plus 60 squared equals 61 squared, that those three numbers indeed satisfy the Pythagorean equation, and that these numbers do also. So that is very strong evidence that our pattern is reliable. So the challenge from all this was find a Pythagorean triple in which the smallest number is 1,213. Well, 1,213 squared is 1,471,369. If you divide that by 2, we have 735,684 and a half. Take a half away and add a half. That gives us the other numbers in the Pythagorean triple, 735,684 and 735,685. And we can easily verify by a calculator or even by hand that this number squared plus this number squared equals this number squared. That means we can have a right triangle with these side lengths, and that this truly is a Pythagorean triple. Well, that completes my solution, but it leads very naturally to a simple follow-up challenge. Here's the essence of my solution. To form a Pythagorean triple, you start with a positive number n. That's the first number of the triple. To get the next number, you square it, divide by 2, and subtract a half. And to get the third number, the c of the triple, you take that n squared divided by 2 and add a half. So the follow-up challenge is show by algebra that these indeed satisfy the equation a squared plus b squared equals c squared. If you can do that, please don't do so at the comments section of this video. Instead, go to my profile page, click on Send Message, and message me your solution. If your solution is correct on the first try, you can have a prize if you want it. The prize that I offer is an audio file of me playing a selection on my piano, a selection that I recorded many years ago. If you want the prize, please request it and include your email address. In any event, I hope that if you work on this follow-up challenge, it will give you some mental stimulation and pleasure. And thank you for watching this solution/challenge video.